Hello and welcome. Today we'll be covering simple pendulums. A few things we already know about pendulums. This mass at the bottom, it's called a bob. And just like our childhood dreams on a swing set, if we were to swing fast enough, it would travel a circular path around the point of rotation. What this means that if the bob was originally traveling in this direction, and at this point was traveling in this direction, there must have been some force going inside. This force is provided by the force of tension in an upward direction at the bottom through the equilibrium point, and as it's traveling here, the force of tension will be directed still towards that center point of rotation. What else do we know? We know it can be used to hypnotize people. That's very important. And the maximum angle, let's call this right here, this angle theta. What theta tells us is the amplitude. The amplitude of this bob is simply this height right here, as if this bob were suspended above this displacement in height between these 2 points. If this bob at this point was to start swinging back, negating friction, the bob should rise to the same change in height if it was following simple harmonic motion. Well, why does it follow simple harmonic motion? Well, we know the force is the same, it's just the force of gravity, but the reason that simple harmonic motion exists in this portion is that a torque is applied as there is a force tangential to the force of tension, except through the equivalence point if we think about it, because gravity is pulling straight down and the force of tension is grabbing straight up. If we were to only move the bob a little bit, the force perpendicular would be slight, and if the bob was moved more outward, this force would be greater. And it'd be the same on the other side, a small force, and as it continues up the path, a larger and larger force would contribute to its x motion, which is simple harmonic motion. This torque is going to change as the angle theta gets larger. But this only works for small degrees. There's a thing called the small angle approximation. And how it works, let's say we have two scenarios. We have a triangle on which theta, this angle right here, is very small, and another triangle in which theta is now quite long. This represents a bob being pushed upwards, and here we have another bob being pushed upwards. What the small angle approximation says is that this length, length 1, and length 2 are practically identical. And we know this because if a bob were suspended right here and it were to swing up, it might go right there. This is different than this, where length 1 and length 2 are significantly different. If that bob were to swing up, it might come here. This length is dramatically longer, and longer proportionately as well, than this length here. So how far can I hold my bob back before it starts to matter? About 12 degrees. And you can notice that from this table, that sine theta and theta are practically identical until we start getting past 12 degrees. Any motion, any amplitude where the bob is drawn back past 12 degrees can no longer be simplified to the small angle approximation, and therefore will not exhibit simple harmonic motion. Okay, so if the force is the same, then it doesn't change, so it's not inversely proportional to the change in x. However, the acceleration is. As we discussed earlier, here we have the force of gravity and the force of tension, and this only exists in the y. There's no x. So why is it simple harmonic? If the ball is brought back slightly, there will be a small x component negative to the positive theta. If we have a negative theta as exhibited by this ball, we will have a positive force, but only just slight, like when you're starting to get going on a swing. If we increase this bob's displacement to closer to 12 degrees, we will see a larger x component to this motion, to this force, and therefore we will start seeing simple harmonic motion between positive and negative 12 degrees with the force, with the acceleration inversely proportionate to the negative theta. Why is it negative? We have a positive theta resulting in a negative force, it's going to the left, and a negative theta, this theta is going to the left, resulting in a positive force. The positive and negative are arbitrary, you could flip them, it would still work, it's just defining left and right. So, how do we calculate the period, or the time it takes for a pendulum to swing back and forth? What matters, what doesn't? Well, we can start with this equation, and knowing what we know with some trig, we can deduce that the period is simply equal to 2 pi times the square root of L over G. Well, what does that mean? Well, I don't see mass in there. I actually don't even see theta in there, which means if this motion were between 0 and 12 degrees, let's call this 12 degrees, and this, let's call this 8 degrees. If these were two balls dropped at the same time, the time it would take this ball to complete its motion is the exact same time it would take this ball to complete its motion. If they were dropped at the same time, they would go back to this point at the exact same time. A little counterintuitive, but it'll make sense after some practice. Mass also does not matter. If you and a friend were to get on a swing set in a frictionless environment and your friend weighed 50 kilograms more than you, and you were simply within 12 degrees of straight down, you and your friend, dropped from the same angle, would exhibit simple harmonic motion and take the same period. What does matter is the length of the rope and the gravitational acceleration of the planet you're on. So this matters a lot because now we can calculate the speed at the bottom. So up at the top, if I'm just holding this ball here, we know this has potential energy. The ball's being held here. It has potential energy because it is being raised a height above its equilibrium position, whatever height this arbitrarily is. I'm going to define it height equals 0. The height it's being raised we see is 1.5 meters. That does not mean the length of the rope is 1.5 meters, but simply the displacement in the y direction from the equilibrium position is 1.5 meters. So mgh is what potential equals. We know the height, and we know our gravitational acceleration. At the bottom, we know it has no gravitational acceleration. I define this height as 0, so its height would be 0. So we know it has all kinetic energy, which is 1/2 mv squared. Well, we don't need to know mass, so solving for velocity, we get that 2gh, the square root, is equal to velocity. Now we just have to find height. How do we find height? Well, we know that this angle has a theta. And this length is the same as this length. So this length, L cosine theta, will give us not this length, but this length, as this forms a right triangle. The advantage of knowing L2, this length, is that if I take L and I subtract L2, I will get what's left over. So if I start with length and I subtract L2, which is this, length cosine theta, I will get amplitude, or the vertical displacement the ball did. So here's some math to calculate that. We find that the height displacement is about 0.304. I guess we're ignoring the example in the previous. Oh, here we go. So it's a 2 meter long rope. It is being pulled back 10 degrees. Well, L cosine theta, we get our height. So we don't need to know the mass because mass is on both sides. We know our g, we know our height. We can solve for velocity. So how does circular motion fit into this? Well, we have centripetal force, which is the force upwards. We know centripetal force is going to be, if we're trying to find the tension, we know the force of tension must be greater than force of gravity, as there's an overall acceleration upwards. As if this was suspended here, the ball would exhibit circular motion. So there has to be a net force towards the center at all times. So the centripetal force is equal to the force of tension minus the force of gravity. How do we find the force of gravity? Well, we know the centripetal force is equal to mv squared over r. We know mass, we just solve for velocity. We know the radius, as it's just the length of the string. Force of gravity is simply the mass of the object times the accelerational constant. So if we know all of these numbers, we can solve for force of tension. You have a physics test coming up. If you're in my class, if you're just watching on YouTube, welcome to the channel. Thank you for watching, and I hope this was helpful.